Bona tarda a tothom i benvinguts en nom dels...
Good afternoon, everyone. We all welcome on behalf of the Institute of Culture of the City Council of Barcelona. We are happy to be with you. The truth is that we are very happy. There were some participating activities as the one held this morning along the river Besòs. We want to get close to science and culture, and we are proud of three things: international talent that we have gathered, gender equality, that's one of the subjects that we are going to address. Most of people are men, and we want to show also that even though we have international experts and talent, we have also local ones, such as the one at the table. She is living in Barcelona, where there are many equipments for dissemination and science divulgation. There is a program called Barcelona Ciencia. This biennial is not new because science and culture is already a classical matter. We want the audience made of people from different ages. The social progress of science is part of culture. We have addressed subjects such as science and aging, art and science, robotics, quantum physics, but not only from a technical point of view, but from the ethical point of view. The 11th of February is the International Day of Women and Kids in Science. Tomorrow we will have up to 100 science schools of Catalonia. They are going to hold a conference, and one of whom will be a Nobel Prize of this table. The program seems to finish tomorrow, but it will last for 150 days. There is the cycle of movies linked to ciencia and phenomena, as well as an exhibition at the Palau Robert. We're going to discuss about the challenges of the science, not only in the past, but also as for gender aspects, which were difficulties faced by women, and whether the ongoing challenges are the same today. The position of women, we are going to address the subject of fake news also, and to talk about this past and present. Apart from the experts, we have our illustrator, Pilarín Valles, who has already started to work. She will dynamize this round table, and her works will be projected on the screen. We have Helen S. Baker. Some of you could attend her talk yesterday. She spent more than 600 hours in the space. She is a doctor specialized in aerospatial medicine. This morning we have had a masterclass by Jerome Friedman about the existence of particles, neutrons, protons and quarks. Another authority of talent, which is linked to the Nobel Prizes, is Morgan Mitchell, who has research about Hersarosh. He created the Institute of Photonic Sciences that we have in Castelldefels. He is a specialist in fundamentals of quantum physics. Ada Ionat, Nobel Prize of Chemistry in 2009, chemical and doctor in X-rays by the Institute Weizmann of Israel, and a pioneer about ribosomes, some studies with therapeutical repercussions. As a moderator, we have José Ramón Calvo. I will introduce him to you. He's Dr. PhD in medicine. He has directed the Immigration Science, Health and Development. He has developed and created el Barco de la Excelencia y director ejecutivo de la Fundación La Excelencia with Nobel Prizes and students. He is an academician of the Royal European Academy of Doctors and president of these institutions, also member of the Academy of Sciences and Engineering. He will hold this debate. We have some hostesses who will give away some pencils and sheets of paper, and he is asking me, since our writing might not be so good, if you can do it in Spanish or in English, it would be better. This will register and be kept in the website of the Science Biennial.
Buenas tardes a todos. ¿Me oyen? Sí, vale. Gracias por estar aquí.
I'm sorry, but the sound is a bit cut. There are some troubles with the sound, at least the sound in the booth.
Ahora seguro que sí. Bien. Digo que
Now much better. I was saying, I was thanking you for this
para venir un domingo por la tarde
marvelous audience on a Sunday afternoon, so I am
lo que se trata es de que hoy
very grateful.
yo les voy a presentar
I will introduce
tenemos en inglés.
you,
Un poco más de
our guests.
eso por la
I will start by
por Ellen Baker.
Ellen Baker.
Es médico y
She's a doctor, former astronaut of NASA. She was heading the Office of Astronauts of NASA. She took part in 3 space missions with more than 600 hours in the space. She graduated in the Bay Heights School in 1970 in New York. She has a degree in geology in Buffalo and a PhD in medicine at the Cornell University, also at the University of Texas in 1994. In 1981, she joined the NASA as a medical officer in the Lyndon B. Johnson Center, and she was selected as an astronaut in 1984. Since then, she completed several works at the NASA for the Space Shuttle and the development of the space station. She worked as a specialist in the STS-15 in 1992 and ST-72 in 1985. She is working in cooperation projects in Africa, mainly in Southern Africa and Mozambique, with women that she helps preventing breast cancer. Ada Yonaf just landed. She has made huge efforts to be here. She escaped from hospital to join us, and she goes back to hospital the day after tomorrow. So, thank you for her generosity. Ada is born in Israel, and she is acknowledged by her pioneering works in the structure of the ribosome. She is head of the Center of Biomolecular of Weizmann Institute, and she was awarded with the Nobel in 1989. Her parents were Polish immigrants. Her father was a rabbin, and they set up in Jerusalem, opening a food shop to survive, although they had many troubles to get through the month. She remembers that books was the only thing she had. In spite of her poverty, her parents sent her to school in Beit Hukarem, guaranteeing her a good education. When his father died at the age of 42, the family was transferred to Tel Aviv. She was accepted in the secondary school of Tishan Haras. Although her mother could not afford the fees, she was teaching maths When she was young, she was inspired in science by the lecture, the reading of the biography of Madame Curie. She went back to Jerusalem, graduating in chemicals in 62, and afterwards in 64, and a PhD in 68 about X-rays studies in the structure of collagen. And since then, she made postdoctoral studies in Boston at the MIT. In 1970, she set up the first lab of proteins crystallography in Israel. Between 1986 and 2004, she headed the Max Planck Investigation Unit in Hamburg. Together with the experiments in Israel, she has worked in several universities in Israel, in the States, in France, and in Germany, mainly focusing on the structure of ribosome, the macromolecules responsible for the synthesis of proteins. Could you tell the moderator to speak a bit slowlier, please? Thank you very much. The most important thing is the Chemistry Nobel Award. She got a diploma by her nephew. She is Academica d'Honor of the European Academy in Barcelona. As our other guest, Dr. Friedman, he is a physicist at the Institute of Massachusetts. He won the Nobel Prize with Richard Taylor for the discovery of the quarks. He was born in Chicago. Her parents were Russian immigrants, and Jerry became, well, he was very good in arts. He had read a book on relativity by Albert Einstein. He refused a grant to study art in Chicago. He preferred to study physics at the university. Whilst he was working there, he was so lucky that he met Enrico Fermi, one of the most important legends in physics. He was the last PhD student. The doctoral thesis was directed by the professor. In the year 68-69, he spent traveling between Boston and California to make experiments in Stanford, leading to the first evidence that the protons had an internal structure recognized as the quarks. That's why he would win the Nobel Award in 1991. We have another guest who is born in the States, although he lives in Barcelona. Quantics optic is his area of work. It is a branch of quantic physics. Max Planck, Albert Einstein, or Niels Bohr devoted many efforts to that. He is a scientist and he is creating, I am greeting the creator, Professor Andreu Mascullet, who has joined us. He got his PhD in Berkeley in 1999 in the group of Raymond Chai, one of the pioneers of this dynamic of dispersion of photon-photon. Studied the mix of four waves. He was in the group of Serge Alloge and Jean-Michel Rimond, the LAP Brussels. He studied the interaction of many things. He got a grant as in 2011, another grant in the year 2016, as well as Vanguardia de la Ciencia in 2012. He is at the head of the IFO devoted to atomic physics for quantic basis. I will start the table in English.
About challenges on science addressed to general public, my first question should be to explain in a short and easy way different concepts that every one of you are experts. I will start with Ada, if you don't mind.
Absolutely.
Ada, can you because you are the last one who arrived, and then I will give you the floor first of all. Can you explain the audience what are the ribosomes and why they are so important for the life?
So there are proteins in our body, in every living cell, that perform almost all the tasks that are needed for life. They function based on their structure, and their structure is based on the genetic code that has the information for their structure. Actually, ribosomes, proteins are made of 20 components, but 20 types of the same chemical entity, but different properties. They are called amino acids, and the sequence of them is what the genes are holding. The information is held by the genes. So there are several proteins that are the same for all the particles from the same organism. And there are some that are personal, like some people are blonde and some are black or white or whatever. This is less important. What's important is what are the functions of each and every protein, and the DNA has this information. The path from the DNA to the protein goes through the factory that can read the instructions and produce the proteins. And this is what the ribosomes do. So they are responsible to almost all the tasks in every living cell, including ourselves.
Thank you. Morgan, could you please to explain the audience what is quantum atomic optics and why it's so important in physics and also for the advancements of other sciences?
Okay, I will try. So atomic quantum optics is 3 words. I'll start with quantum. So I think probably most people know that quantum physics is what governs the microscopic world, electrons, protons, quarks even, and everything that is made out of them. So atoms, molecules, ribosomes, and us eventually. Quantum physics is a very famously difficult and non-intuitive theory. It's something which is difficult to understand, and it becomes more difficult to understand as the object becomes larger. So then I can get to atoms and photonics, or atomic quantum optics. That optics is the science of light or the science of photons. Atoms are atoms. We attach these to the quantum physical principles. We study them because they're very simple. And so that gives us a system where it is possible to see all of the unusual, all of the surprising things in quantum physics in a very clean way. What does this do for the world? Well, first, it gives us information about quantum physics, which is intrinsically interesting. I think it's a fascinating theory. It's something that I think very few people in the world would even claim to fully understand. But at the same time, it gives rise to new technologies. There's a lot of interest now in quantum technologies. Quantum technologies use the unusual features of quantum physics in order to produce things. For example, extremely fast computers or very secure ways to communicate information, knowing that it cannot be intercepted by anyone in between.
Thank you very much. Recuerden que habrá gente por ahí con papelitos.
Remember that there will some people distributing some papers in case you would have a question.
Ellen, the people are normal, the general population are fascinated about the space and the space career, etc. My question is to start this discussion. Can you refresh the people how the space career has started, the origins of that, and especially how the space research has been an advantage and for the humankind regarding the topics and the things and the issues that has been discovered thanks to this space career?
That's a long question.
Yes, I know.
My colleagues here work with things that are very small. Space is very big. And as long as there have been people on Earth, we've looked up at the stars and wondered what's out there and how do we fit into this grand universe. But it wasn't really until relatively recently, 60, 70 years ago, that we were able to travel off of Earth. And the initial space race, our first vehicles among the US and the Russians, were really fueled by the Cold War. We both wanted to get off the planet and into space first. And if you remember, the first orbiting object was Sputnik. And it was about this big, not very big, but it made a little beeping sound as it traveled around the world, and it threw the United States into panic. And the rest is sort of history, as they say. So the Russians and the Americans were racing to build rockets to get people into space and ultimately to get a man to land on the moon and then return safely to Earth. And in doing so, we discovered new worlds off of our planet, but we also discovered new technologies, very much like all the research that goes on, be it for very small things or very big things. And I think our exploration of space and our development of space technology is here to stay. And we are looking at going further beyond low Earth orbit now, perhaps back to the moon, perhaps to Mars. And in terms of robotic space missions, we have sent vehicles to both ends of the solar system and have even had a few vehicles leave the solar system. So we're really just scratching the surface of what's out there. But with our new telescopes and things like that, we can look far, far into the past and across the universe.
Thank you. Jerry, the last but not the least.
Okay, no, it's perfectly okay.
My question for you is very easy, obviously. It's about quarks. Can you explain our audience about what they are and why their discovery was so important for the science?
Okay. This morning I gave a talk titled, "Are we really made of quarks?" And the answer is yes. Because, for example, we're made up of atoms. Atoms have a nucleus made up of protons and neutrons, and each neutron and each proton is made up of quarks. So quarks are some of the fundamental building blocks of the universe. And as a result of discovering quarks, we also have a new theory of how protons are held together and how nuclei are held together, called quantum chromodynamics. So it's a very fundamental law, because in particle physics, you not only want to understand the fundamental building blocks of the universe, but also the forces that they interact with. And so quarks now are part of the so-called standard model, which is the current model of fundamental interactions. And it could not have occurred without, we could not have had this model without having quarks. But in addition to this, if we think about the evolution of the universe and cosmology, it turns out that in the very early period after the Big Bang, very quickly after the Big Bang, the universe was a high energy physics reaction with quarks and gluons and everything like that interacting. So actually understanding quarks also gave us some information about how the universe evolves. So quarks play a fundamental role in both our understanding of the fundamental laws and particles, but also in the evolution of the universe. Now the question is, why do we do that? We try to understand where we come from, what is going on in the universe. That's the human quest. In addition to this, as pointed out by Ellen, the science that tries to understand these things at a very fundamental level also has marvelous and very highly developed spin-off technologies. We don't know whether quarks will ever have any kind of application. It's too early to know. But however, whether they do or not, we know that the spin-offs from the investigations have had enormously important applications in society. So let me say the following. Quarks are a fundamental idea which actually pervades our idea of how the world is constructed.
Thank you very much. Well, as the title of this roundtable is around challenges on science, I think that our next question should be address this important issue, that is, each one of you, what do you think that could be the most important challenge in science in each one of your fields? For example, in the case of Ellen, that now is working as a physician and helping people in developing countries, what do you feel that could be the challenge in the area that you are now working on about health in women?
You might not like this answer, but we are trying to build old, easy technologies into the infrastructure of places where it doesn't exist. So we don't need fancy new drugs. We need the ability to offer to people in the world who don't have it some of the very basic tools for prevention, screening, and treatment of disease. There's many places where there is very little medical infrastructure, and that's the main challenge that I am working with now.
And can you explain a little bit to the audience about the kind of job that you are doing there in these countries, in South Africa and Mozambique, please?
I'm actually working not in breast cancer, but cervical cancer, which is a preventable disease. In 1995, it was discovered by Harold Zerhausen that cervical cancer was caused by a virus, the HPV virus. And we now have very good ways to prevent this cancer. Not many cancers you can prevent like this, but we have vaccination against this virus, and we have screening so that you can detect precancerous changes in the cervix and then treat people for it. But in many places of the world where the population is very poor and the medical infrastructure is very weak, women do not get vaccinated and they don't get screened. And so we are trying to help build those programs in places where they currently do not exist. Mm-hmm. And in doing so, we will save many lives. Cervical cancer used to be one of the most common cancers in the United States and in other developed countries, but now with the introduction of screening and now vaccination, it's way down on the list, maybe number 14 or number 15, so it's much less common than it used to be. Still number 1 in many places of the world for women.
Mm-hmm. Thank you. Morgan?
So a major challenge for quantum technology or for quantum optics. So I think probably the target which is most important to people, or which at least gets the most attention, is the possibility to build a computer which is based on quantum optical principles, which in some way uses the very strange feature of entanglement in order to be able to compute much faster and to compute problems which we currently cannot compute. One of those problems, for example, is to understand how molecules form and the dynamics of molecules, something that would go directly into, for example, medical research, could benefit medical research. The way that we're trying to do that is by building quantum physical systems and connecting them up, much the way that in a regular computer you connect up transistors in order to make circuits, in order to be able to do ordinary computations. Now we're connecting up quantum physical devices, for example, superconductors or atoms, and we want to see them do something similar to a computer, but at this quantum level, which will allow them to work much faster. There's an important challenge there, which is that we don't know exactly how superconductors work. We don't know exactly how atoms work when they are networked together. And this gives us a problem, and that's exactly the kind of problem that would be well solved if we had a quantum computer. So we find ourselves with what the computer people call a bootstrapping problem. That is, you have a problem that you could easily solve if you already had the solution to that problem. And that means you need a breakthrough. And that's what we are looking for, and we are trying very hard to find that breakthrough. It's not completely different than what happened with regular computers, that now when you want to design a new microprocessor, you use the old microprocessors in order to do a simulation of the new microprocessor before you build it. And so that way you can intelligently design the microprocessor, not by making many, many designs and seeing which work, but by simulation. So we're trying to get to that point where we have a quantum computer which can help us to build better quantum computers.
Thank you. Ada, what do you think about challenges in your field? You have a lot of them. I have a question for you later, but now I will.
There are challenges all over all over life, all over nature, and I really don't like the word most. Because what looks most at one point can be less most when another most is found. So let me tell you what I think is a challenge. So, as I said earlier, proteins are performing almost all tasks. In human, for instance, let me give you 2 or 3 examples, like breathing, or the blood that takes the oxygen from the lungs to wherever it's needed, insulin that controls the blood sugar, and so on. The same is also in bacteria. Bacteria needs to breathe and grow and become twice. It means make the second generation. And ribosomes are the factories that produce all these proteins. So if one wants to get rid of bad bacteria, bacteria that causes infections, and in the past even simple infections were killers, one can stop the ribosome. And indeed, most of the antibiotics, or at least half of the antibiotics, are stopping ribosomes. So, and they are clinically used. And there is a lot of resistance to them, and resistance grows from day to day. Antibiotics came into usage in the middle of last century, around 1950. And in the beginning, there was a whole activity of big companies. They made them better. Antibiotics themselves, especially the ribosomal antibiotics, are made by bacteria. Companies try to make them faster, less poisonous, and so on. But resistance is growing. Bacteria are trying to fight against the antibiotics, and they are doing it very well and very effectively. And we as human beings are suffering from it, and so far there is no major company that took any strong and persistent way to make new antibiotics. So I see a big challenge to fight against resistance. Antibiotics are also problematic because they are not only killing the bad bacteria that cause the infections, for instance. And by the way, from infections, probably you know better, but there is a lot of casualties and death. Even all those that have cancer or related diseases, some of them die just because of some type of infection that they cannot, their body cannot fight against it, and there is resistance for the bacteria that causes it. So this is a big problem, not, as I said, not only because of infections themselves, also infections of ill or immune weak people, and also because the antibiotics do not distinguish between the bad bacteria and the good bacteria that is in our body. It's called the microbiome. that is very important for our health. Also, most of the currently used antibiotics contain cores that are not digestible and not degradable. So when they go into the soil after we don't eat them, we cannot digest them. They are so small that most of the penetration, most of purification systems cannot catch them, and they are contaminating. Don't you think it's a big challenge to make new antibiotics?
Of course. Probably it's the bigger one. Jerry, what about you?
Oh, there are so many challenges, I don't know where to begin, because, when you're trying to understand the entire universe, both at the largest distances and the smallest distances, there are so many things you do not understand. For example, we only really have some understanding of 5% of the substance of this universe, namely atomic matter. There are other two things going on there which we have really no idea at all of what they are. Something is called cold dark matter, which represents roughly about 25% of the universe substance, and the other thing is called dark energy, which is roughly 70%. And we just have no idea what these things are, and it's going to take immense amounts of research to try to understand them. Now, it turns out that, the universe is expanding. Ever since the Big Bang, it's expanding. And this dark energy actually is causing this expansion to accelerate, and that has been observed. So we know it exists, and that is very perplexing. Another big problem is how to reconcile quantum theory and general relativity. We just do not know how to do it. People are trying it at string theory, but string theory is a valiant attempt and it's making some progress. But the problem with string theory is that it's at an energy level that we cannot test. Namely, if we consider the current accelerators, for example, the LHC at CERN, that's going to go to about 14 trillion electron volts, which is an immense amount of energy. But it turns out that string theory is being developed at an energy which is 15 orders of magnitude beyond it, which means that this energy is multiplied by 1 with 15 zeros after it, by that number, and that's the energy which string theory is being done. So it's a very perplexing issue as to how to unify these two. And it's going to be a big challenge. And of course, the other issue is, what about experimental work? Well, the major problem in particle physics is that, as I pointed out in my talk this morning, that the smaller the thing that you want to investigate, the higher the energy. In fact, it's linear with energy. So if I want to measure something 10 times smaller, I've got to get 10 times more energy. And we are running out of energy in the following sense: it's getting very expensive. It's now we can only have a multinational instrument, namely, for example, CERN is a multinational, and that's the only way we can go, and that's fine. But at some points, even that may not run out of money in terms of trying to understand things at a more fundamental level. So and maybe some new technology will come, which will make this technology possible to get the very, very high energy. But we don't see it in sight. So there are many, many challenges. It's a marvelous field because it encompasses everything. When I talk about particle physics, I also really want to talk about cosmology and astrophysics because they are very, very intimately related.
Thank you. We have here several questions, but I would like to ask our two ladies here. Everyone knows that Helen was 3 times at the space, but I would like to ask Ada and everyone in the audience will be that this gentleman drinks something before to go here. But how many times have you been related to the space, on the space, Ada?
I've never been in space.
I know.
But
you know why I'm asking such question.
But we ran 23 different experiments.
Yes.
during about 15 years in space with very little result. Some result, and we learned a lot, but the success that we were looking for did not come.
But can you explain a little bit some of these experiments, how was the performance, and especially because you have an astronaut near you, and then you can make some discussion about that? That probably the audience will love to have this discussion.
So in order to understand how any molecule works, one has to know the structure of it. And until recently, and even today, the main technique to find out the structure of biological molecules, and also not biological, all molecules, is crystallography. So I'm not going to explain crystallography now, but from the name, it's clear that it needs crystals. And to crystallize, no problem to see crystals of salt when you buy salt, the salt that you put on salad. But to crystallize particles like ribosomes was a big challenge. Many tried to do it and failed when I started. I don't want to go into all what we did, but at one point, when we already had crystals, they were not suitable for measurements because they were too thin. They had reasonable dimensions, or what we call reasonable dimensions. It means about 0.5 millimeter on two sides, but on the third side, crystals have to be periodic in 3 dimensions. So in the third dimension, they were much too thin, and we could not handle them, and also we couldn't get the right phenomena, which is the diffraction. So we thought, because the third dimension, the crystals grew as plates, and they always were stuck either to the bottom or to the ceiling of the drop where we grew them. So we thought that there is something to do with gravity. Either depends on which conditions we used, either they go down or they go up, they get stuck to something and they don't go in that direction. So we thought about trying to grow them in microgravity, and this is what happens in space. Microgravity, almost no gravity. So we tried. We approached NASA, and then because we were in Europe, they told us we have also to talk to ESA, which is NASA in Europe. It didn't matter. They were very, very excited about it. For, as I said, more than 15 years, we had contacts with them. We tried lots of missions. The first one was Chinese, but afterwards they were mainly going out from Cape Kennedy in the United States. And we put experiments on all of them, and many other crystallographers, protein crystallographers, joined us until NASA decided that they want to make a whole direction of it, like an institute for this. And this went on, and only one example from about 25 or 30 scientists, with each of us, at least as we had 20 experiments or 25 experiments, some had even 30 or 40 or 50 because the compounds they used were not as complicated as ours, and only one result, one good result. So you see, sometimes in science there is great idea, there is great work, there are great people to help, there are great techniques, and not everything works.
Ellen, do you have any comment?
Did you know about it?
We actually had crystallography experiments on some of my flights. My second flight, Larry DeLucas flew with us, and I don't know if you know him. He's a protein crystallographer from the University of Alabama. So we did several experiments, yes. Space is a really good environment to do some of these experiments. When you remove most of the force of gravity, you have a very unique opportunity to do things that you can't do very easily sometimes here on Earth. The problem with space flight is there's limited space in the space station and on the space shuttle, and we can't accommodate all of the science and all of the investigators on Earth who would like to fly their experiments. It's a problem.
That's exactly correct. The space in space is
Yeah,
limited. The actual space in space
there's not a
was
lot of
limited.
room inside the space station or the space shuttle to accommodate all the great ideas and all the experiments proposed to be operated in orbit.
Okay, we'll start with a question from our audience, and one of them, the people are concerned about the fake news on science. Oh, please.
May I just make one comment? Because I
Yes.
think there's a general problem regarding all science that we haven't really touched on. And I think it's one of the most important problems in science. And that is the reluctance in political leaders to invest in basic research. And the idea, everybody talks about innovation, innovation, innovation. But the most basic and the most revolutionary innovation comes from new knowledge. And new knowledge cannot be obtained without basic research. Now you go talk to the government leaders and they say, well, can you promise me this? What's going to come in 5 years? Can you promise me a result? And of course, you cannot. That's the whole thing about basic research. It's curiosity driven. You try to understand it. You take false directions sometimes. You go down false streets. However, and in fact, if you don't make 2 or 3 errors of judgment, you're not trying hard enough in the area. And so there have to be failures, but it has to be vigorously supported. Curiosity must be honored and supported. And so I always say to government leaders, well, I can't promise you such and such. However, I can look back at the past and tell you what has come from basic research. For example, in the late 1800s, people looked at spectra from various elements, and they found line spectra. Didn't understand it. Then there was Rutherford, who studied and found the solar system model of the atom. And they didn't understand it because it conflicted with classical physics. Then came quantum mechanics to explain that. And it turns out that probably the most important physics result in terms of invention of the 20th century was the transistor. Because the transistor led to the microchip. And can you imagine a world in which we don't have microchips? Half the economies of developed nations depend upon microchips. But the point is, without that basic research about curiosity, we would never have had the transistor and the microchip, and we would never have all the things. The cell phone you carry, the internet, your computer, even your washing machine now uses microchips. And I mean, everything. And so I really want to get this point across to you as citizens, that when you talk to political leaders, tell them how important it is to invest in basic research. And it's an investment, it's not a cost, because economists have looked at all the data about economic growth, and they say that kind of investment pays back much better than Wall Street does.
Ada.
So I want to join you. I agree fully with what you said, and I have another example. This is electricity. Before there was light, people used candles. And there was a lot of non-basic research how to do the candles better. Better light and longer life. This didn't work. But several physicists looked at the let's call it the transport of electrons between 2 anodes and cathodes. And from this, we have later on, after basic research, we have electricity. But in the beginning, nobody thought about electricity when people started to look. And those guys that tried to make better candles are still trying, I think.
Morgan, have you any comment about that?
I completely agree. I think basic research is extremely important. The example that I would give is the invention of the laser. The Nobel Prize in Physics this year was given for applications of lasers, which include eye surgery, treatment of cancer, and if when the laser was being studied, you would ask the scientists, please find me a way to improve people's vision or to cure cancer, then nobody would have believed that research into amplification of light, which is what gives us the laser, would have given that. The investment in that time was not directed toward any particular goal. It was directed toward understanding what happens when you have material and light in interaction, and it gave rise to these applications, which are fantastic. So I completely agree that investment in basic research is something which pays back in a very large way, and is something which is easy for people to forget about, but it needs to be kept in mind.
Thank you. By the way, we have a question from the audience, who is probably it's good to ask now, because it's what are the political challenges to open and transparent science, and where we can do what we can do. This is the question that someone asked to us. What are the political challenges to open and transparent sciences, and what we can do?
You say transparency?
Yes.
Well, science is all transparent because it has to be published. I'm not quite sure what the reason for this question is, but it's not like military science where things are kept under secrecy. Because every scientific result, if it's going to be considered a reasonable scientific result, has to be published. And of course, it's only considered correct if other people read it and can verify it, because one observation isn't sufficient to make for a scientific result. And therefore, science is very careful to check what's going on. Of course, there are people sometimes who fabricate, and they are discovered ultimately, but that is quite rare, and all science is by nature transparent.
Any other comment?
So one aspect of the open science question is whether anyone can have access to the scientific results. And it's true that when they're published, then anyone has the right to have access to it. But if it's with a journal, if the copyright is owned by a journal, then you have to pay to have access to it. And people that are associated with wealthy universities, then they easily have that access, but the general public does not easily have access to that. They cannot afford to subscribe to all of the journals that contain this information. There is a movement to change the way the journals operate so that the published results are available to everybody who wants them. It means changing the way that the journal's costs are paid. It's not going to be paid by subscription. It will be paid by other mechanisms. This is something which, in my opinion, the public should demand, because there are results that the public paid for, that when the research is paid for by public money, then those research results should be public property, and they should very much support this push for open access to research results.
So perhaps the political aspect in the question is related to some countries that don't let all the papers to be read. They don't allow all the flux of new results becoming available. Maybe they thought about it, and I fully support complete transparency in every country.
Ellen, do you have any comment about that?
No, I agree.
Okay. Another question. Should we start to learn in Chinese to participate or understand future high-level science talks? In probably another way, it will be the Chinese, the leaders of science in the future? What do you think? Jerry?
Well, I think it's it's very difficult to learn Chinese. I've looked into it to some degree. And, at the present time, for better or worse, English is the international language of science. It's a historical accident. It turns out that it seems to work. Even Chinese who get involved in international science know English. Certainly true in Japan. And so I think unless there's even if China becomes a very big powerhouse in science, there's no need to change it because it would be such a big disruption at this point in the history of science. I think it wouldn't be worth it. It would be just a sort of a nationalistic kind of symbol, but it's not going to help science. And I think that for better or worse, we have a working system, and maybe in the future it'll change somewhat depending upon circumstances, but I don't see Chinese coming in as an international language of science.
Mm-hmm. Okay. Another question for all of you. Should knowledge be free to access, meaning journals to be free and anyone could read any paper without paying?
You want to?
Yes.
Yes.
I think
I would say yes.
Very well over there.
He answered already.
Yes. All of us.
But I'll tell you, there is a problem, and the problem is that somebody has to pay for the basic machinery to get the thing published, and that we have to figure out, and that's where part of the problem is. I remember I was once an officer in the American Physical Society, and it would very much like to have free journals, but it can't publish the journals unless there's some income coming in. So the question is, unless you have government or private donations doing it, it really can't happen because it just can't be free. I mean, there is a lot of work involved in publishing a journal. You have to hire editors. You have to have it printed. Maybe even now with the internet, the printing isn't so bad, but you still have to have editors, and you have to have people who basically read the papers and so on and so forth. So I think we have to figure that out. But I think it's a good objective to have.
So how about companies that sell scientific equipment, scientific whatever, publishing in these journals and holding it from the point of view of what you said, money, support?
Yeah, some area of support.
If people think about it this way, maybe they can. I think that the journals should be interested in publishers like this, not in us paying them from time to time and asking, we don't have money, maybe we cannot, and so on.
Another question about that is said, what do you think about pay for publishing? Some journals who request you to pay just in order to be published. This is another question that apparently there are people here who are concerned with.
Oh, that's terrible. That is absolutely terrible. It's so anti-scientific because imagine developing countries who have a scientific community who are trying to get into the scientific community of the world and they want to publish. They don't have money to pay publishing houses. It's ridiculous. I mean, that is terrible. That's one step above the idea of paying for journals. I mean, that is something that really should be stopped.
So, some journals actually waive the fee in developing countries. The New England Journal will not charge a subscription fee for low-income countries, for physicians in low-income countries. So, in that way, it's good access, particularly for people who can't afford it. But that also goes for paying for publication. There's a waiver of a fee for some of the journals that do ask for a donation for publication. But I think that it's dangerous in introducing bias into what gets reported if that's the system that you have.
Morgan, have you any comment about that?
So I agree that there's an important problem there, that you do not want to price anyone out of publishing. I think the journals, especially the ones that are run by professional societies, have an interest in I don't know exactly what to call this, but equal access to the power to publish, that it's not in the society's interest to exclude scientists of any kind. And so I hope that they will be able to find a pricing model which makes it still accessible to everyone.
Thank you. Another general question. Someone asked, challenges of science is the same that challenges us for a new model of society?
Can you repeat, please?
Yes. The challenges on science are equal to the challenges for a new model of society?
A new model of society is much harder, much harder, because you've got to convince many people in very, very strong vested interests. A new model of science basically will have a lot of resistance initially, but if the experiments turn out to support it, it will be ultimately accepted. And this has happened in many cases. I mean, for example, the whole idea of quarks was terribly resisted, was thought to be a pretty bad idea when it first was proposed, and people looked for quarks and couldn't find them. But ultimately, when the experimental results came in, there was no question that quarks existed, and it was accepted ultimately by everybody, and is now the basis for doing physics. A new society is a very difficult issue. Imagine, let's say 25 years from now, when robots take over 40% of the jobs, and people will not have incomes. A large part of the population will not have incomes. How do we support them? What do they do? What kind of society do we have? That's a challenge, and that's something that society will have to contend with. But that'll be difficult, I can assure you, because you can see that whenever any kind of social innovation occurs in a democratic country, the amount of controversy and back and forth, the discussion is just immense.
Okay. Ada, do you have any comment?
I fully agree. It's much more of a challenge to have a new society. But if I go back to the politicians and science for a minute, which is somehow related, one of the reasons that the politicians are reluctant to invest, to put their money into basic science that takes a long time, is that we have democracies. They have to be re-elected in 4 years or 5 years, depending on which country. They have to show that something happened during this time if they want to talk to the public to be elected. So maybe we can get away from the need to show scientific results in order to be popular politically.
Any comment? No? Okay, another question. What can do regular scientists to protect a culture of science and rationality in the Western world? This culture is under attack. This is the question. Some comment about that?
Well, maybe I'm talking too much. I'm sorry. I'd be happy if somebody else to start. I apologize. But the only way to do it, and the scientists have a big role to do in this, and namely, scientists have to engage the public. I know it's not easy, but they have to engage the public and tell the public about science and have them understand science and have them, because otherwise politicians can say anything about science and there's nothing to counter it. I mean, this is happening in the United States right now. We have a political party that doesn't believe in global warming, and it's a disaster. Unfortunately, that political party controls the presidency. And so the question, and now, for example, a number of states are independently trying to stay within the Paris Accord, though the federal government has withdrawn. But I think it's very important that the public continually be told really what's going on, and the only one who can do it are scientists interacting with journalists, because journalists have access to millions of people where scientists don't. But it's very important that we play the role. It's also very important that we go and see politicians as often as we can and do our best to persuade them. It doesn't happen by magic. It takes a lot of hard work.
And I'll also say that it's really important for children to get a good education in science, to be a good citizen, no matter where you are, because you can find anything online that supports your point of view, no matter how off base it is. And so I think education is really, really important for everybody. You don't have to be a scientist, but you have to understand enough about science to be a good citizen.
I think I agree with everything that's been said until now. For me, the example which is most clear is the resistance to vaccines in some places. That there are parents who make the decision not to vaccinate their children against diseases that are easily preventable and are serious diseases, and they must make the comparison. This is what my neighbor said, or this is what I read in some article online, and this is what my pediatrician says, and I'm going to believe the article online instead of believing my pediatrician. And this, to me, speaks to a lack of confidence in science among the public, at least among some parts of the public, that is really profound. That someone could look at these different points of view, the rational model that's proposed by science, that's backed by lots of evidence and lots of studies, versus someone's opinion on the internet, and decide that they're going to go against science. I think engagement has to be the answer to that. I think we cannot be far away from the public. I think we cannot be in our ivory towers basing our authority on the approval of our peers. We also have to reach out to the people if we want them to respond to the things that we have to say.
Another question. What, in your opinion, keeps girls away from academia? Older men, perhaps? Can you answer something, Ada?
First of all, I know many girls in academia. Maybe I'm wrong, but at least in my group, 70% are girls, more than half.
I think it's a lot different now than it was actually when I was in college even, but I think women are very well represented in almost all fields of science, and Jerry told me today about half the class at MIT now are women. So, and I think engineering is probably one of those fields where women haven't entered as rapidly as, let's say, medicine, where now probably more than half the medical students are women. So I think there have been a lot of good changes over the last few decades, and that should not be a deterrent anymore.
I think that the society is telling women that it's difficult to be scientists and housewives or mothers. So it's mainly not the girls themselves, but those that gives them advice, or the parents, the teachers. So this is at least in my opinion. But if one thinks about it, science is demanding from men and from women. But also politics is demanding, and art is demanding, and dancing is demanding. It means if one wants to do what one really feels, it's demanding, but there is payment for that, and there is take back from this. So the society should change the attitude, if at all. But now, as you heard, there are more and more girls, so maybe all what I'm saying is not important anymore.
Any other comment? Here is a question made by a teenager from the audience, and said for everyone. What encouraged you to follow your studies and not other purposes when you were teenagers? Thanks.
You want me to start?
Yes.
Okay.
Please.
Well, when I was in high school, I was an art student. I really wanted to become a painter, and I went to a special high school in Chicago, which allowed me to draw and paint 3 hours a day, and I was happily engaged. I didn't take much science. I took very little mathematics. And what really got me involved was I think at the end of my 3rd year of high school, I went to a museum in Chicago called the Museum of Science and Industry, and I picked up a little book written by Albert Einstein about the meaning of relativity. And it was something I always wanted to understand. My parents, Albert Einstein was a household hero in those days. And I heard about these strange things about moving clocks slowing down and moving meter sticks shrinking. And I said, how can that be? It seems so weird. And so I picked up this book, and I spent the whole summer going through it. I did take algebra so I could do all the so-called Lorentz transformations. And at the end of the summer, I said, gee, this is really interesting, but I still don't understand it. And as a result of that, I decided I'd like to go to the university and try to understand it and maybe get involved in physics. And I had a scholarship to the Museum School of the Arts of Chicago, which I refused to take, and I went to the University of Chicago. I made my art teacher very unhappy because he had written a letter for me, et cetera, et cetera. But as I look back, it was because I was curious. I got engaged by some trying to understand very basic and important science, and I never looked back after that. And as I look back at my career, I'm so happy I took that direction. I probably wouldn't have been a very good artist. I still paint on my spare time, but I've had the pleasure of trying to understand some of the most difficult things in science. I'm not always successful, but I've worked hard, and it's been tremendously inspiring. So that's what happened to me.
More or less the same story, but I didn't go to the Chicago Science Museum because I was in Tel Aviv. I wanted to be a writer. I wanted to write books. But I tried to write what I felt, and it never came out the way it was inside me, burning. It was so difficult for me to become a writer, so I became a scientist.
I wanted to play baseball. It's true, I wanted to play baseball for the New York Yankees, and it really bothered me that there were no girls playing professional baseball, and I never once thought about being an astronaut because that was just impossible. And when I was young, it was only boys who got to be astronauts. So here I am all these years later. I never thought in a million years I could be an astronaut, but my daughters still could not play baseball for the New York Yankees.
So I don't think I have a story to tell about my high school years, but my first year in university, I was looking for a summer job. I had missed all of the deadlines to apply for opportunities to work in laboratories, except for one, and I applied to that. And it was at Northwestern University, which is in Chicago. It was in a laboratory that was doing immunology. But for me, that meant I was working with bacteria and viruses and DNA. And so I was growing bacteria, infecting them with viruses, extracting their DNA, and then putting it on a gel so that it would have these bands, and I could see the individual letters of the bases of the DNA. And this was fantastic. This was wonderful. I was much too young to be qualified for doing this work. There were 3 graduate students in the lab. They were all Catholic women, and they looked at me, this young guy, and they said, "Oh, he's so cute, he's so small, he's so young, he doesn't know what he was doing." And so they were kind of mothers to me. I was there in Chicago, away from home, away from university, and the social interaction was also very, very interesting. I saw people whose careers took off during that summer, and I saw people whose careers crashed during that summer. And it was a summer that had a bit of everything in it. There was fantastic science. I got to see things that I'd only read about in books. I had all of these people around me that had these fascinating relationships amongst each other, and I was hooked, and I knew I was going to be a scientist.
Okay. I will do the last general questions, and then after that, as we have a short time now, I will address one question to each one of you that has been sent by the public. The general question was probably from a teenager, also a student. What would you tell or recommend to young students who want to work and do research on science?
Want me to start?
Yes.
I would say, go for it. Because I think doing research in science is one of the best jobs in the world. Look, you get paid for solving puzzles of your own choice. What if you like crossword puzzles? Somebody said, oh, you can do whatever crossword puzzle you want, and I'll pay you for it. That's what science is. You propose your own puzzles, and you try to solve them. It's really a wonderful career, and especially if you get into academia, you're also teaching some of the brightest minds in the world, and it's very stimulating and it's wonderful. And of course the subject matter is wonderful. But there's one thing you have to be very careful of it. You've got to go into the science you truly love. You really have to do something that you have passion for and you can dedicate yourself to. So you have to really love the subject.
So I can only add to what you said one advice. I have only one, and this is don't look for advices. Do what you feel. This is interesting for you. You have curiosity for. You're ready to get yourself into, and you can do it. But don't look for advices.
And I would say similar, find something you really love and that you're passionate about, and you never know where that will take you. But work really hard. Science and engineering are not easy. You have to be willing to really put your nose to the grindstone and really work hard to do a good job. But find something you love and really go after it.
I like everything that's been said until now. I think the one thing that I would add is that when you start doing science, it can seem like there's just one skill that is important. So if you are doing physics, it might be your ability to solve equations seems like the only thing that's important. But in your career, that will not be the only thing that is important. You will need many, many skills. And so if you are good with people, that will be very important in your scientific career. If you're good at writing, if you're good at art even, that will be important during your scientific career. And remember that you will need to draw upon all of your skills, and if you're like most people, then there will be some part of science that you are not good at, because most people are not good at everything.
Okay. Now, questions for each one of you. Helen, the question is for you. When you were in space, did the group behave differently socially than on Earth?
Actually, on my 3 flights, I would say we interacted fairly normally in space and on Earth. But there's a lot of preparation before a space flight. You spend a lot of time with your crew, both in Houston at our home base and traveling and training. And that translates very well to how you behave on orbit. And I will say, as a testament to our training, that being in space, even though we were floating around the space shuttle or in the Russian space station, felt very much like we were on Earth going through our training. So I would say it was fairly similar, and I would think that most crews would agree with me.
Okay. This question is for Ada. Which is the major challenge you have overcome as a woman, as a person, to become a scientist?
I don't know if there was one. Surely not as a woman. As a human being, maybe I had some difficulties. Not everything I did worked the way I wanted. In the beginning, when I started, I didn't even expect that I will get result because many others failed. So I have lots of stories, but nothing to do with the woman eyes.
Morgan, a question. Have any utility the quantic computer more than the codification of keywords and spy activities?
Yes, okay, so that's, breaking codes was the first application that was identified, and that is, of course, something which is very interesting to certain parts of the government, and so it got some funding. But lately people are working on ways to combine artificial intelligence and quantum computing. So, for example, there have been large advances in artificial intelligence, for example, recognizing images, recognizing faces, analyzing large amounts of data and finding patterns. And this is something which can be done better if you have a quantum computer than if you have a classical computer. And so this promises to be in some sense a much bigger application, because at the same time people are also working on codes that you cannot break with a quantum computer. And so it may be that they started out with one possible application and they end with a different set of possible applications.
Mm-hmm. Jerry, the last question in this round is for you. As a member of the atomic scientists, what is your view of the existential risk posed by nuclear weapons?
There's an enormous risk, and I think we have to pay attention to it, more so than we have. And the ultimate objective is, of course, to rid all of the planet of nuclear weapons. It won't be easy, because, there's always the issue of terrorist groups, unfortunately, who might have access to some of the technology, and we have to be concerned about that. But that is the objective, and we should work very hard to accomplish that.
Okay. There on a topic that several questions about the fake news. And the question is also general again. How do you think that the fake news affect the science and the believer in science of the most of the population who read only newspapers or go to internet as the new Bible? What do you think about?
It's a big threat. Like I said earlier, no matter how crazy your idea is, you will find somebody else out there who provides support and gives credence to whatever your crazy ideas are. It's I think a real issue. I think you have to be very careful about where you get your information and make sure it's a credible and accurate and honest source. And I think there's no controlling it. I don't think you can get rid of it. That's why I think we need an educated public so you can discern what is fake and what is not fake.
Okay. Jerry?
Well, I think, for example, one of probably the greatest threat to humankind at the present time is climate change. We see the effects starting now. We see the effects now, and it's only going to get worse, according to all predictions. And yet there are people on the internet who say it's not happening, or if it's happening, it's a natural thing, and there's nothing we should do about it. And we have to work very hard to try to correct that. And again, it has to do with scientists interacting with journalists as much as possible and with the public, because the only way to counteract fake news is to give them the correct news and from authoritative people. And there is no substitute. So we have a big challenge here.
Mm-hmm. Any other comment about fake news?
So fake news is clearly a large problem. I just want to note that it's somehow a product of something that we should think ultimately is good, which is that the internet allows many people to transmit information to many other people. The problem is that that capacity got there very early, and then bad actors have been using it in order to distribute information that is not in the interest of society. The majority of the knowledge-generating community has to get active and do something about this, but I would hope that in the long run, the existence of the internet, the access to all of this information will ultimately be good for society.
Okay. And I have time for, I think, a couple of questions more. One is very funny. Said, do you think each one of you that exists life out of the earth? Of the earth. Yes.
Yes, sure. She was there.
Yes, next question.
A lot.
A lot of stars, a lot of planets, a lot of opportunity. Will we ever meet our neighbors out there? Maybe not. The universe is really big, but I think the likelihood of life out there is not significant, but I think it's definitely there.
Do you have any opinion? Ada, would you like to add something?
She was there.
Yes.
How can I add something to somebody that has experience?
A question here, it's, let's see, because there are a lot of them that probably we have no time to do it. This is a more general also, is the human science are developing very quickly, probably thanks to advances in another science. A lot of people think that it's difficult to make a difference between the knowledge and ideology. What do you think about?
Well, should I start?
Yes.
I'm sorry. Look, if you have scientific knowledge, it has to do with observation. I mean, that's the basis of science. And if we don't have observation, we don't have science. So if you have what you call scientific knowledge about social issues, it should come from observation about the opinions by people. Of course, it's got to be done carefully. It's got to be done with the right kind of statistical accuracy. But that's the only way to counter ideology, because ideology is just basically a point of view. It isn't based upon observation.
Mm-hmm. Any other comment? Okay, then I have the last question before to introduce my friend Pilarín Valles, who is ending her fantastic job. The question is, could the science answer which part of the amount of things that we already know, which part of the things that we already know can be answered by the science? It's a rhetorical and difficult question.
Repeat that again. I'm not quite sure.
No, can the science answer which part of all the things that we already know?
If we know what we have to answer.
Yes.
That's the question.
The question was, can the science answer which part of the total amount of the things that we already know?
But the question is, how do we know it?
Yes.
That's the issue.
Yes.
So you have to specify that.
Yes, I think that this is true.
Yeah, well, look at if we know it by observation, then it is science. If we don't know it by observation, that basically it's conjecture, and that science can actually make comments about it, or correct it, or change it, or whatever. And that's all there is to it.
Any other comment? Well, I think that we are on time now to give the word to our friend Pilarín. She is ending. Pilarín, ¿estás lista para?
Pilarín, are you ready to tell us something?
Okay.
I was the worst student in science in my school. I was the worst student of science in my school. Can you understand what I'm saying? But I knew that Parufet was the first astronaut, and he was Catalan, and it was produced by a fart. And I believe that this is quite an strange thing. You know what? I do believe that we must be very, very thankful to Allah, because you tried to escape from your bed because you were ill, and now you are amongst us. I think that you have a very good look, and you already overcame your illness. I believe that we must be also very, very thankful to Anin, because she was in this space. I was the first that I was here, and she thought that women breasts are causing a lot of problems. Therefore, it was great to help other women. Thank you very much. And no, I don't need any applause. I think that he's kind of a grandparent. It's like your granddaddy that is telling a story to his granddaughter, and he's talking about the phenomena of the Big Bang, which is a very difficult thing to understand. And I think that he's the man that is tempted to be like Michelangelo. When he is almost ready, he's wanted to tell the robot, hey, talk. The only thing that you need is to talk about. Okay, and this one, that's you. And an angel is telling you, you are like I'll be when I'll get older. Okay, so it's like a good angel that is helping everybody here to have this discussion in a peaceful manner without fighting against each other. And here we have other ideas that suddenly came to my mind. We have God theoretically invented everything, and he prefers to look up to the computer because things are very difficult to him. And here we have the evil. Then he was the creator of fake news, for sure. He's the evil, and here we all together, we need to ask governments to give funds for research. Yeah, I got it. Gotcha. That's needed. And when we talk about the work of women, that we need to make possible the work that we developed as man does. We have a robot. She is not a feminist, but this girl is already feminist, this robot girl. And that's all. Thank you.
Gracias. Bien. Después de esta sesión que espero que les haya gustado,
I hope that you enjoyed and it was entertaining and you had fun. It is to me a great pleasure. Well, we had a stack of questions here where some of them were more specific than others, but I tried to pick those that were more interesting for everybody. Otherwise, anyway, I'd like to thank you all for being here, and I hope that it was worthwhile, and that you had fun this Sunday afternoon sharing the awesomeness of these four guests and our amazing Pilarín Valles. Thank you very much, and thank you very much for coming.
El senyor Calvo em demana pujar a l'escenari, simplement agrair-vos la participació.
I'd just like to thank you on behalf of the Cultural Institute of Barcelona. I'd like to let you know that tomorrow we have more conferences, workshops. Please take a program because we have more than 50 activities in more than 60 venues. Thank you. See you next time.